path integrals are really all about understanding the unitary time evolution operator, which is called the propagator when you look at it in position representation. And that's all the path integral really is. It's just a different way of expressing the solution to the unitary time evolution operator in position space for when you have a Hamiltonian that's, naturally written in coordinate representation. So it's time evolution for Hamiltonians, which look like, p squared over 2m plus some potential. That's the setting. And there's no time dependence. It's actually kind of hard to put a time-dependent perturbation in a path integral problem. I won't really be talking about that. So that's why it's a little bit confusing, is because we were talking about time-dependent perturbation theory. Well, now we're just going to talk about stationary Hamiltonians that don't have any explicit time dependence. But we're still going to study this object, the unitary time evolution operator, just for a time-independent Hamiltonian. So we know that we can exponentiate the Hamiltonian and get what we need for the time evolution operator. And the last thing I was doing is I was using this property of the unitary evolution. So in position space, if you sandwich the unitary operator between, and let's say it goes from some t to some t prime, this we argued is equal to the inner product between the Heisenberg eigenstates of the position operator in the Heisenberg picture. We argued that it's just this inner product. Where each of these states, the xt is an eigenstate of the position operator in the Heisenberg picture. Because remember, in the Heisenberg picture, you put the exponentiated Hamiltonian on either side of the operator. So that's what this U will do. So that's what we derived. And we derived a composition relation for this operator, namely, or for this position space representation of this operator, namely that you can stick in a bunch of intermediate positions and times, and that doesn't change the value of the inner product. We can break it up into a bunch of short intervals. Like this, all the way out to x1, t1, xt. So we just stick in a bunch of completeness relations and get this composition property that you don't have to take an inner product between two times that are far apart from each other. You can just look at a product of these little propagators over infinitesimal time differences. And that actually lets us, for Hamiltonians of this type, it lets us calculate what the propagator is. So that's what we did sort of towards the end, is we said, well, okay, let's look at what happens over a very short time interval if we evolve from the state xt to some time a little bit later, t plus delta t. And of course, that's just the exponentiated Hamiltonian. And we spent some time calculating this and expanding in small delta t. You go to linear order in delta t. So you expand the exponential, then you re-expand the exponential. And so maybe I'll just go through a few of those steps. Then you also know that you have a p here, so you want to stick in a completeness relation over the momentum states. So once you do that, you get, of course, the plane wave functions. And you get, so we expanded in small delta t, and then we undid that expansion and put everything back into the exponential. Once we have replaced the operators with their eigenvalues, it's the usual thing. You want to act with the operator. You want to, when you have an exponentiated operator, you want to expand it outright. Then you have the operator act on its eigenstate, and then you just have numbers left over, and you can do whatever you want with those. And since we only care about the solution sort of to leading order in delta t, we can just re-exponentiate the delta t. It doesn't change the approximation to sort of linear order in delta t. And so we were left with the re-exponentiated Taylor series that looks like this. And now it's v of x little x, the actual variable, not the operator. So we were left with this kind of thing. And so now we just have to perform the integral over p. And as I mentioned, this is a, it's a Fresnel integral. It's a sort of imaginary version of a Gaussian integral. You can factor out this part, which doesn't depend on p. So you got this part, and then you got the 2 pi h bar. And then you have this integration, which looks like a Gaussian. And as usual, it's convenient to write it in such a way where you can obviously complete the square to do it. So you have a linear term in p here, this term here, and then you have the quadratic. So it's like a imaginary Gaussian. But really, it's just called a Fresnel integral, and its convergence properties are pretty well understood. But basically, what you do is you analytically continue the stuff out front here to lie on the real axis instead of along the imaginary axis, and then you can just perform it as a regular Gaussian integral. But the idea, again, to get rid of that linear term, you want to rewrite it such a way that the linear term is kind of hanging out here next to the quadratic term. And in that case, you can now just complete the square. So as an aside, again, the relevant integration here is just a Gaussian integration e to the minus alpha, z squared plus beta z. And again, our alpha is imaginary, but that doesn't, actually doesn't matter. And it's from minus infinity to infinity. And what you do is you complete the square in the exponential. You just, so it becomes minus alpha And instead of z, we get rid of the cross term by subtracting beta over 2 and squaring. And the cross term will be, this is, I guess, plus. The cross term will be just beta over 2 times z, which is beta z. And then you, of course, have to subtract off the extra term that you introduced, which is beta squared over 4. So that's the idea. Then since z is integrated over all values anyway, then the shift doesn't matter. So all the linear term does is just contributes an extra exponential factor. This is from the pi over alpha is from the integral over z, and then you're left with this cross term, which is, this extra term that you introduced, which is the minus signs cancel. It's just alpha beta squared divided by 4. So that's what you get. You can now use this because this integral has that same form. You do have a square root of an imaginary number. That's fine. We know how to do that. You can just write it, in terms of its phase, e to the I pi over 2, and then take the square root. It'll be, plus or minus I pi over 4. So you can use Euler's formula to figure out what that is if you want. But it really won't matter for our purposes because it'll just be a constant out front. So, okay, so applying this, we get that our propagator here is equal to in the exponential, this stuff out here, and this is 2 pi h bar. Now there's a square root from the Gaussian integration, which is 2 pi m h bar over I delta t. And then we have the leftover exponential from that linear term that we took care of using completing the square. And that term is I delta t over 2 h bar. That's this alpha part. And then we've got, we have 2m, we have the beta squared, right? So we have 2m squared x minus x prime squared over delta t squared, and there's a factor of 4. This factor of 4 there. Okay, so this is actually very nice because factors cancel, and what you get is you get a nice form. You get square root of m over 2 pi h bar I delta t. And then you have the exponential. And now you can combine back the potential term and everything else. There's a common factor of I delta t over h bar. And you get minus v of x from the potential part. And then out here, okay, so one of the m's cancels, the 4's cancel, and you get m over 2. That's from this 2 over here. You get m over 2, and then you have x prime minus x squared. Or x minus x prime, doesn't matter because it's squared. Delta t squared. Well, now if you just stare at this thing, you recognize that if your time interval delta t is vanishingly small, as we send this to 0, and these are the locations of the particle over this delta t interval, then what this is just a change in the position of the particle squared over the time interval over which you're looking at squared. So this is just the velocity squared. And as we all know, 1/2 mv squared is the kinetic energy. So this whole thing then is the kinetic minus the potential energy. This whole thing is the classical Lagrangian. And so this formulation using the propagator is a way of connecting quantum mechanics. It's the quantum mechanical version of Lagrangian mechanics, which you would study in classical mechanics, the sort of more advanced version of that class that goes beyond like F equals ma or whatever. So it's the classical Lagrangian, and of course it depends on the position and the velocity, and the general form of it for the kinds of problems we'll be worried about mostly is just 1/2 mv squared x dot squared time derivative squared minus the potential. Okay, any questions about that? That's sort of the important part of deriving the path integral. Everything else is just using that composition formula. Any questions about that? You might be unhappy with the fact that we took this exponentiated operator here and we Taylor expanded it to a linear order in delta, and then we exponentiated it again in terms of we exponentiated it again and turned it back into an exponential. It seems kind of ad hoc, but it's not really. You could do it sort of more formally if you're unhappy with that. You can also show that the exponential of this kind of Hamiltonian, you could just, using that exponential of operators formula where you write things in terms of commutators and stuff, the Trotter formula, we saw it in the first semester. We're looking at basically the exponentials of a plus b and connecting it to the product of the exponentials. And we had corrections here that had to do with the commutator between a and b. So you can sort of do the same thing here. And basically what you conclude is once you take the commutator, right, you'll have two factors of t, and if t is small, then order t squared, that commutator term won't do anything. So you can basically just use the formula, or let me put this delta t just so it's clear that this is a small t. So you can actually just expand the exponential out into a product of the kinetic and potential terms. And then the corrections that you get due to the commutator are small. So you get something of order delta t squared. That's the correction. So you can do it that way. I just didn't feel like doing it because I didn't want to calculate commutators and stuff. I prefer to do it this way, but this also kind of assumes that, you know what you're going to get, because what we did was just expanded this guy to linear order, and then we re-expanded it to get essentially what you would have gotten if you just expanded out the exponential like this, because now this exponential can act on the momentum eigenstates, this exponential can act on the position eigenstates, and you end up getting the same thing. Okay, so let's apply now the composition rule to this result. Now we know what this looks like at each infinitesimal time interval, and we know that we have to integrate up all of the infinitesimal time intervals to get the result. So nothing really is stopping us from going back here and just doing that. So we're gonna now use our result and put in all of the explicit values of the infinitesimal propagators. So you get a bunch of integrals from 1 to n over the intermediate coordinates. Now, of course, for each of those, you get this prefactor out front. You'll get n plus 1 of them. So if you count the number of propagators, right, it's not n of them. There's actually n plus 1 of them in here, because we have n coordinates, but if you just count how many propagators you have, because of these states that are sandwiched between here, you'll actually get an extra propagator. So there's n plus 1 propagators. If there's n of these completeness relations, right, then, but they get sandwiched between the two states, so you pick up an extra propagator. Hopefully you can see that as just simple counting of the number of these inner products. There's n plus 1 of them. And the exponentials, when you multiply them together, well, they all add up, because products of exponentials are, you just sum the exponents. And we don't have to worry about operators now or anything, because the propagators themselves are already in position representation. So everything's in terms of coordinates. There's no operators anymore. Everything's classical. Everything commutes. So this is it. You would get a sum. And what is the sum? Well, it's the sum of the Lagrangian at each of the time intervals. And of course, as you make the number of time intervals infinitely large, and you start partitioning your time interval from t to t prime over sort of smaller and smaller segments, you stick in lots of these completeness relations from t1, t2, and so on all the way up to tn. So you get more and more of them, you'll just get a sum, right, over all of them, of the Lagrangian at each of those intermediate time intervals. Well, if you put in enough of them, they'll be sort of infinitely closely spaced, and you'll get just a Riemann sum for an integral. Actually, in the limit that delta t gets smaller and smaller and smaller, you'll get just the integral. And I forgot, of course, the delta t. There's a delta t here. So just plugging in the solution here. And this must be the the classical Lagrangian evaluated at at the time at the interval time. So if there might be some issues in where precisely you evaluate it at what particular time, but it won't. You sort of won't worry about that, because we're going to make these times infinitely closely spaced, and it actually does sometimes matter which particular time. It might talking about the the first time or the latest time of the intervals. There's some that can be important actually, but we're just going to go to the continuous time limit where we don't really care, which kind of Riemann sum we use to approximate the integral. We're just going to say in the limit it just converges to the integral. But just so you know, there is important issues, especially when you deal with noisy systems where the noise is of a particular kind, and you do have to worry about when you evaluate the stuff in the exponential. But that goes into the realm of kind of stochastic calculus, which we sort of won't really get into. But the point is, you can now say, well, okay, fine. If we make enough of them, then maybe this just in the limit becomes an integral over time. And what we're left with is what's called a functional integral. We can think about this thing. What's this thing? This must be the integral over all the intermediate coordinates. And in the continuum limit, there's an infinite number of them. So it must be over all paths. So these x's, the x of I represents the coordinate of your system at time t sub I, right? So we must be integrating over all of those. There's a prefactor out front, which we can just absorb in the integral measure, just as a normalization. And so we can call this, just by definition, so this is what it actually is, but we can call this as a sort of shorthand as a path integral, which is the integration over all paths taken by x, where t bar ranges from your initial time to your final time, and this part becomes the exponential of I over h bar, just the integration from t to t prime of the classical Lagrangian, which again depends on the coordinate and on its time derivative. So we have reduced now the computation of a propagator, which tells us how quantum mechanical states evolve in position representation. We have converted that to a sum, if you want, over all possible paths of that particle as it goes from time t to time t prime. And each path is weighted by this complex phase. And this complex phase is given by I over h bar, an integral from the initial time to the final time of the classical Lagrangian. And so you can actually use this to like compute time evolved states. It's basically another way of solving Schrodinger's equation, right? This is a solution to Schrodinger's equation. Remember what the unitary operator does. It just tells you how states evolve, right? We can use this propagator, right, to take, let me call it k, right? X prime, we could, take some initial wave function, integrate it against k, and that'll give us the wave function at x at the evolved time. So let's say just over time t. If the initial time is say 0 and the final time is t or something like that. That's what it is. It gives you, literally just gives you a solution to the Schrodinger equation. This thing is a solution to right. Okay, so that's great. And we'll actually try to compute something. We'll try to use this to actually calculate something for a particle, and do a free particle or something. But you see, this is hard to do. It's usually the path integral, you don't really use it to solve the time-dependent Schrodinger equation all that often. Sometimes you do for certain cases, but mostly it's a conceptual tool where you recognize that in some sense, a quantum mechanical particle, when going from two different times, instead of like in the classical case where it would just follow its equation of motion along a specified trajectory, and that's how it'll move. In quantum mechanics, the probability of observing a particle at some position, given that it's at some other position at your initial time, that probability actually consists of, or the probability amplitude consists of, a sum over all the possible ways in which the particle can go from one point to another. So it's, in a sense, instead of, the idea is if you start with some particle at x and t, and it goes to some other point x prime at time t prime, then classically what would have happened is it just would follow some trajectory as specified by its equation of motion. Whereas what quantum mechanics tells you is actually you have to sum over all the paths connecting these 2 points, where each path is sort of weighted by this phase factor. And what basically will happen is, as your system goes closer to the classical limit, the paths that will contribute the most to this probability are the ones that are going to lie along the classical trajectory that you would have gotten from just solving the Lagrangian dynamics, right? From just getting the equations of motion from the Lagrangian. You can sort of see that over here. What will happen is, the classical limit, would be an appropriately scaled h bar, right? I mentioned you can't just send things with units to 0, but if you scale this appropriately, you'll have a 1 over h bar type thing, and classically it would mean that this contribution is sort of much bigger than the h bar. So what will happen is h bar will be quite small, and so this exponent will be, for the most part, large. And if it's large, then it'll oscillate very quickly, right? If this is large and sort of quickly varying, right, then I times a large number that sort of changes quickly, it will be a very rapidly oscillating function. And so the places, the paths for sort of small h bar that contribute the most will be the ones for which the quantity in here varies slowly. Because if it's large and varies quickly, then those oscillations will just cancel each other out. And so basically what will happen is, as h bar goes to 0, the main path that contributes this will be the one that extremizes this integral. If you remember from classical mechanics, this is just the action. And if you extremize it, meaning you find it sort of where the critical points are, where it's slowly varying, it's like first derivative test. If you remember your calculus of variations, if you extremize the integral of the Lagrangian, you just get the Euler-Lagrange equations, right? You get the equations of motion, the classical equations of motion that you would get from a Lagrangian. Okay, so that's kind of conceptually what's going on. Let us now do more explicit calculations, I guess. Any questions about that, though? Okay, so again, the basic idea here of what a path integral is, say in one dimension, you look at all of the possible positions at time t of the particle, starting with some initial time and going to some final time. Those are the sort of time, that's the time interval over which your unitary operator goes, and you start with some initial state which is fixed, and then you're looking at some final point which is also fixed. And then the idea of the path integral is that you slice up this time interval into a bunch of infinitesimal slices, and what you do is the path integration is just the integral over all of the possible positions. So here's one possible trajectory, right, that this thing could have from the initial position to the final position. So what you want to do in the path integral is you want to integrate over all these intermediate positions. That's what we're doing. And so that ends up basically being an integral over all the possible paths from that point to the other. So that's what this is. That's what this formula is. And for each path, you sum up the value of the Lagrangian at those intermediate points, and if there's an infinite number of them, that just becomes the integral of the Lagrangian over that path. So that's what it is. So let's do an example. Of course, the easiest example that you could think of is just where the classical Lagrangian is just 1/2 mx dot squared, just free particle. Now, if we fix the initial and final positions, which we do for the purposes of calculating the propagator, we know that the classical path is what? What's the if I were to put in white the classical path here between these 2 points, if this is the Lagrangian, what would it look like?
Would it be a straight line?
That's right. It would be a straight line, because if the only energy is the kinetic energy, then it'll just move with some. That's the only thing you have. If it's just the kinetic energy, and that's going to be conserved because that's the total energy, then all that can happen is it just has some energy. So it has a fixed velocity, and it just moves with whatever that velocity has to be in order to get from this point to this point. So that's all it can be. That's right. So it's just a straight line. That's the classical path. So you can actually just write what that is. That's just the initial position. Okay. That's the initial position plus whatever the velocity has to be in order to reach that final point at time tf. So this is just a line. This is an equation for a line. It's just written in sort of, I guess, point slope formula or whatever. This ensures the right boundary condition, right? When t is equal to ti, you're at the initial point, and when t is equal to tf, then these cancel and you're just left with fx minus xi, and the xi's cancel and you're at the final position. So that's what we would expect classically. But of course, quantum mechanically, the particle, in some sense, it's the probability amplitude associated with moving from that initial point to the final point is a sum over all the possible paths, not just the ones that have constant velocity, all the ones that don't conserve energy, that do all sorts of crazy things. Basically, any path going from the initial to the final point. And so quantum mechanically, the probability amplitude for going between these 2 points is, again, it's given by, well, this path integral. And we're going to write this path integral in a particular way. It's convenient since we have these final and initial points fixed, it's convenient to write this trajectory as a kind of as the classical trajectory plus a little bit, or maybe we'll call it delta x. Now, from the point of view of the path integral, this doesn't change anything. It's just a variable change. It's a variable change because we're going to integrate over all possible functions anyway. So what does it matter if we just shift all our functions by the classical path? It doesn't do anything. It's like adding a linear function to all your paths. It doesn't matter since we're integrating over all possible paths anyway, so that doesn't change anything. So instead of integrating over all paths, we can integrate over all like delta x's instead. And then what's the Lagrangian piece? Well, it's the exponential. There's a Im over 2h bar. It's just the kinetic energy. It's the integral from Ti to Tf. And now it's Vt bar. And the Lagrangian is, well, there's the part that comes from the classical piece. That's going to be the velocity squared. Remember, the classical piece has just a constant velocity, and it has to be the difference between the positions squared divided by the difference in the time squared. That's just v squared. And then there's going to be, of course, the contribution that comes from these deviations, which is delta x dot, the time derivative of delta x's squared. Okay, so now this classical piece, it comes out. And what we get is this guy. Times this leftover integration, this leftover path integral over all the deviations away from the classical path. And this is even the extreme deviations, like the really wild ones. And the leftover integral is just Im over 2h bar integral Ti Tf of just the time derivative of that delta x dot. So what else? Now we would have to do this leftover integration. The issue is that this is kind of a hard integral to do, right? Because even this guy, it's not so trivial to do because you're integrating over all possible functions, delta x, and sure, they have a nice boundary condition, namely that delta x at ti and tf has to vanish. That does make things easier. It has to vanish because the classical path already takes care of the boundary condition here, the beginning and the end. But it's still hard to do, and I'm not going to do it. But you can do it. I mean, see, this is why path integrals are hard, because you don't really want to do an infinite number of integrals most of the time. That's normally much more challenging than just solving the Schrodinger equation. We could have just solved the Schrodinger equation for a free particle and gotten this anyway. But you could do it, and you can see that this also kind of has a Gaussian form. So kind of unsurprisingly, once you do this integration, you get a square root of, the 1 over the stuff out in front here. But I'm not going to do it. Maybe I'll do it in recitation, but I won't do it right now. What you get is, from that leftover Gaussian integral, is a square root of m. Oh, sorry, yeah, you get the square root of the stuff that's in here, not the inverse. It's then there's a factor of there's some factors of pi that come up, but in any case, you get you get the following. After you do this, you get the square root factor, which yeah, I might show you that in recitation if there's interest. But then you have this exponential part, which we got from the classical path. And that's your propagator. Now you can use this to evolve any initial wave function that you had. You can evolve it to find what happens to it under free particle evolution. You could take this result and integrate it over all the initial states. And you could take this thing, which, xf tf, this exact expression here that we just derived, you can take it and figure out what the wave function is doing. After, if you started out initially at this time as this guy, whatever your initial condition is, you can use it to evolve the wave function. And let's see what happens. Let's see the way in which the classical path starts to contribute, right, the most, when we assume, quote unquote, h bar is small. So let's see that. So let's suppose that our initial wave function, this thing, let's suppose this thing is some envelope function. And let's assume it's got some initial momentum like that. So this is like a wave packet, right, moving with some initial momentum p naught. So let's see what happens if we put in all of what we know. Let me not put xi, there's too many indices running around. I'm just going to put, instead of xi, x bar. It's just a dummy variable of integration anyway. So we have m over 2 pi I h bar. And now let me say that ti is equal to 0, initial time is 0. And again, we're going to put xi is equal to x bar. And the final time, we'll just say we're looking at time t. So we're just evolving from time 0 to time t, just to make the notation a little bit less annoying. So then we substitute stuff in, we get this. We get this guy, im over 2h bar. Now it's going to be x. And let's say we're looking at the final x is just at some x. So it's x minus x bar squared divided by t. T. I think I'm actually missing. Let's see. Where I think I'm off a little bit, right? Let's see. Yeah, I'm off. I'm off here. You see, so this part has to be. Yeah, I'm off here a little bit. The classical path is. I'm missing a factor of. Yeah, I didn't do this integral, right? If I integrate this, right? Once I do this integral, I get this constant multiplied by TF minus TI, the range of integration. So I'm missing the fact that the classical thing just has one power of TF minus TI in the bottom there. Sure. I don't know if you guys caught that. That's yeah. So when you integrate this, right, you multiply this by TF minus TI. So one of those factors cancels. So this is actually just over T, not T squared. Okay. So, and then this is all multiplied by f of x bar now, e to the I, p naught x bar over h bar. Okay, so now what? Now we argue that if h bar is really small compared to the rest of this stuff, then what will happen is the contribution to this integral will mostly come from the place where the stuff inside the exponential is slowly varying, where it satisfies the first derivative kind of test. The first derivative with respect to x bar here is equal to 0, where it's slowly varying. Because if the thing is varying quickly, if it's got a sort of non-zero derivative, then if h bar is small, then that'll lead to large changes in this exponential, and it'll make the exponential oscillate a lot. And that'll give you a lot of positive and negative contributions in both the imaginary and the real part, because those are just sines and cosines. And so it'll cancel out. So as h bar goes to 0, and again, to do this properly, you want to rescale by some characteristic length and energy scales. But if you did that, then you know that, what will happen is that this whole integrand in here, all this stuff in here, the major contribution will just come from the place where x is slowly varying. So I can say approximately this is equal to m over 2 pi I h bar t. And now we're going to say the integral is done with, and all that happened is that we picked up the place where x bar is sort of gives us a stationary point. So E0 x star, and I'll show you what the stationary point is in a moment. So I combined exponentials here, and this is f of x star. So what's x star? X star is that stationary point, and to get it, we just have to do the first derivative test. So we just have to do d dx bar, stuff in the exponential. All the stuff in here. And if we do that, then what do we get? Well, we get, well, you can see here, right? So what we get is the derivative of this guy, which is 2 times x minus x bar times the derivative of the stuff inside, which is -1. So from this term, we get minus I m over h bar. The 2's cancel. We get x minus x bar. And from here, the exponential part from the momentum, we just get I p naught over h bar. And the first derivative kills the x bar. So just get that. And we don't worry about the f because the f doesn't have any factors of h bar in it. So we're not worried about that. That's just coming along for the ride. That's not oscillating very quickly. It's just some smoothly varying envelope function. And so this has to all be equal to 0. That's how we find the stationary point. We just say, okay, all the stuff in the exponential can't vary very quickly with x bar, the variable which we're integrating. So we just find the points where the first derivative vanishes there. That's the place where, you know, it doesn't change. Well, that's very easy to solve. X bar here, which is now x star, the stationary point, that's equal to, solving this is x minus p naught t over m. And if you look at this, this is nothing but another line. It's, you know, the x bar, or if you want, x, the final point we're looking at is related to the initial point, x bar, via plus v naught t, just a linear function of time. And that makes perfect sense because this is a free particle. So if we start it with some initial momentum, some initial velocity, then in the classical limit, it should just obey, just go in the straight line, right? With time according to its initial velocity. So, and that's what this tells you, right? This path integral approach tells you that although all paths contribute to the probability amplitude like this, in the classical limit, it's sort of easier to see in the path integral that the path that will contribute the most is the one that extremizes the action. Or if you remember that from classical mechanics, or if you see explicitly here for the free particle, when we put everything in and set h bar to 0, then or we made h bar small, then we see that the dominant path comes from the stationary points of this action, which is, again, the same sort of extremizing it. And at these stationary points, the paths are just straight lines, just constant velocity paths. All right, and so then you can use that to, of course, just, I mean, now you're kind of done, right? Because now what you get is that, well, you get your solutions. Psi of x of t is equal to m over 2 pi I h bar t, the exponential of I m v naught t squared over 2 h bar t. And then you get the initial wave function evaluated at x minus v naught t. Right? If we just plug in for x star here, this becomes v naught t squared over t. That's this exponential part. And then, well, then yeah, then you get The rest of it is just this guy, the initial wave function evaluated at the stationary point, which is x minus v naught t, this guy. And that's just a shifted initial wave function. So for a free particle in the classical limit, all that happens is the wave function just shifts the original wave function by a constant amount. And then there's just an extra phase that gets picked up. That's not physical. And then there's this funny normalization, and you might be worried about that because it looks like the wave function is not properly normalized now. But actually it's fine because I did the stationary approximation in a kind of ad hoc way where I just got rid of the integration and said, well, the integration is going to mostly have contributions at around the stationary point. If I were to do it properly, I would expand around the stationary point and then perform the integration. And that leftover integration you get after expanding the leading order around the stationary point would be a Gaussian integration. And that Gaussian integration will end up canceling the square root. So in the end, you would get a normalization, but yeah. Any questions about that? So that was a little bit of an example. And we can now say something a little more general, but any questions before I clear this? Okay, so what about generally? So there's some interesting applications of the path integral. And one thing to consider is that if you have a path, right, x of t, and you perturb it a little bit, you take it to some x of t plus some delta x of t, that doesn't change the path integration, right? Remember, as I said, as I've been emphasizing here, we sum over all possible paths. So if we shift our paths by some amount, like the classical path, that doesn't change the result. It doesn't change anything about the path integral because they're still summing over all paths. It's like doing a variable change where you take x to x plus 2, and if you're integrating x from minus infinity to infinity, it doesn't do anything to the integral. But you can use that then to derive something interesting. Namely, you know that then if you do this integral change, then and now let me write, instead of the integral of the Lagrangian, I'm going to write it as S. The action, S, is just the integral of the classical Lagrangian. Then, if you perturb by this amount delta t, and so you look at Lagrangians of paths that are modified a little bit by some delta x, or equivalently the action, then we know that if you subtract off the path integral where you don't make this shift, right, then this can't do anything. This must be equal to 0 identically, because, as I said, it's just like a linear shift. Or it's just like adding a constant to a variable of integration, where the variable of integration is just integrated over all real numbers anyway. That's point by point along that path. That's what you're doing. So that's not, that's doesn't do anything, doesn't change the path integral. But this is actually very powerful because we can now assume that this thing is small and start doing Taylor series. And if we start doing a Taylor series, then this thing becomes, if we look at the first term in the Taylor series, this will be the integral dx of t of, again, exponential I over h bar. Now s evaluated at just x, and then the linear, the variation, and then you'd have the derivative of what's in here, which we're going to write as I over h bar delta s, where this is the leading order term in if you Taylor series expand in delta x, right? The 0th order term will just cancel this part, and the first order term will give you this, and this is equal to 0. And I'll tell you what this is. Delta s is just, of course, the difference in the actions, the perturbed and unperturbed actions, which if you do the calculus of variations, you might remember from classical mechanics, it's just the integral, put a bar here, of the Lagrangian with differentiated with respect to x, and then this guy, all multiplied by delta x, the variation in the path. That's just from the calculus of variations. And so we can conclude, right, that if we plug this back into here, if we plug this back into there, what we find is that the integral d of x of t of e to the I over h bar s. Now, if we substitute in for, okay, and we have the I over h bar. Now we just substitute in for that delta s. We get the integral dt bar of the Euler-Lagrange equations, which you should be familiar from classical mechanics. If you go back to the derivation of the Euler-Lagrange equations from extremizing sort of the integral of the Lagrangian, you'll sort of get a memory jog of where this comes from, just from the calculus of variations. I can go over it in recitation also if necessary. Okay, and then this is all times delta x. And now, and this is all, of course, equal to 0. And moreover, this doesn't depend on the particular kind of perturbation that you apply, right? The variation was arbitrary. We just assumed it's small, but we can make this, for instance, vanish everywhere except where t bar is equal to some arbitrary time t prime. And so we can actually make this integral vanish. This expression has to hold basically for every point along the integration, because we can make this delta x such that it vanishes everywhere except at any given point along the integration. And of course, this is all equal to 0, so we can drop the I over h bar, and we conclude that the integral over all paths that the particle can take of the Euler-Lagrange equation. Remember, this is a thing that you would set equal to 0 to get the equations of motion for a classical particle. Now what we're saying is that something similar to that works in quantum mechanics, except it's not that this whole thing is equal to 0, it's that the integral over all paths of this quantity, the Euler-Lagrange equation, weighted by the action, that's what's equal to 0. So yeah, this is like the quantum version of the Euler-Lagrange equations that you would have seen in classical mechanics. So it's not true that, you know, this Euler-Lagrange equation just works like it would in classical mechanics. Instead, the quantum mechanical version of that is that the Euler-Lagrange equations are true only in an average sense, only in this sense where we integrate over all paths and each path is weighted by this by the action. Okay, I don't know if this equation is used all that often, but I wanted to make more clear the connection between classical Lagrangian dynamics and what we're doing now with the path integral. The path integral gives you the clearest connection between doing Lagrangian mechanics and quantum mechanics. Because again, what it does for you is it allows you to express the quantum mechanical propagator, which tells you how wave functions evolve in terms of the classical Lagrangian. It just says that instead of evolving according to a classical Lagrangian in quantum mechanics, a particle probability amplitude consists of contributions from all possible paths weighted by the action, which is the integrated Lagrangian. And the classical limit here comes about when the most dominant contribution to the motion of that particle comes from the classical path. When your sum over paths is dominated by the classical one. And that happens when h bar is somehow small compared with the characteristic length and energy scales of that are in your action. So, and then you can use the stationary phase approximation to show that more rigorously. But I just want you to get the concepts of this, not necessarily the details of stationary phase or anything. That's not that important. So yeah, I think I'll leave it here. And then next time we'll do the more applications of this. We'll do Aharonov-Bohm, and we'll also talk about how path integrals are used in finance.